Before we start this event, allow us to say thanks you very much to the Department of Chemistry, Riau University, Chemistry Student Association, and we also thanks to our sponsor, Sentra Karya Bertuah Cluster, which is one the companies engaged in the property sector. Without all of you, this event could not run smoothly. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Muhammad Abdul Karim. It's a precious chance for me to be your master of ceremony on this very special occasion. Chem Talks exceeds expectations, potential, and increase the science through chemistry. First of all, best wishes to all of us, and let's say thanks to God Allah Subhanahu wa Ta'ala, who has given us guidance, happiness, healthy, blessings, mercies, and graces, so we can attend and participate in this special event without any obstacles. Secondly, peace be upon to our Prophet Muhammad Sallallahu Alaihi Wasallam by saying Allahumma salli ala Sayyidina Muhammad wa ala ali Sayyidina Muhammad. The Honorable to the speaker, Dr. Nobutaka Yamanaka from National Defense Academy, Japan. The Honorable Dean of Faculty Mathematics and Natural Sciences, Riau University, Dr. Shamsuddha. The Honorable to the Head of Chemistry Department, Dr. Muhdarina. The Honorable to the Organizational Board of Trustees of Chemistry Student Association, Soni Ananta. The Honorable to the Head of Chemistry Student Association, Irgi Ahmad Fahrezi. The Honorable to the Head of Committee, Muhammad Haikal Zikra, and Honorable to all of participants. Welcome to our international webinar with the topic is bimetallic catalyst for chemoselective transformation of nitroaromatic compounds. On this special morning, we have several agenda as follows that you can see in our screens. The first agenda is the opening, and the second agenda is the opening remarks from the Organizational Board of Trustees of Chemistry Student Associations. The third agenda is speech by our speaker, Dr. Nobutaka Yamanaka. The fourth is Q&A session, and the last is closings. Well, ladies and gentlemen, let's begin this event by National Anthem of Indonesia, Indonesia Raya. Please respect and pay attention to all of participants. Thanks to your attention. Next agenda, we will present an introduced video from our major chemistry department, Riau University. The committee time to show.
Universitas Riau is one of public university located in Pekanbaru. Founded on October 1st, 1962, Universitas Riau is celebrating its birthday this month with various exciting events, including this international webinar. Faculty of Math and Natural Science are one of the 10 faculties in Universitas Riau. Department of Chemistry is one of 5 departments under this faculty. Department of Chemistry has undergraduate, magister, and doctorate program. Both of undergraduate and magister program has received A accreditation from Indonesia's National Accreditation Board for Higher Education. Department of Chemistry of Universitas Riau aims to create high quality and competitive graduates in Southeast Asia on 2035 and to be one of the best research center in both life and non-life natural resources. Our research focused on 5 key areas. First is Amir Awaludin, Dr. Nur Hayati, Dr. Amelia Linggawati, and Dr. Leo Saputra. biocity. Has undergraduate, magister, and doctorate program. Both of undergraduate and magister program has received A accreditation from Indonesia's National Accreditation Board for Higher Education. Department of Chemistry of Universitas Riau aims to create high quality and competitive graduates in Southeast Asia on 2035 and to be one of the best research center in both life and non-life natural resources. Our research focused on 5 key areas. First is catalytic conversion on biomass and waste treatment, led by Professor Amir Awaludin, Dr. Nur Hayati, Dr. Amelia Linggawati, and Dr. Leo Saputra. Bioactive compounds from local biodiversities, led by Professor Titania Nugroho, Professor Saryono, Dr. Hilwan Yuda Teruna, Dr. Rudi Hendra, Dr. Yohana Nurulita, Silvera Devi, Andi Dahliati, Yuli Haryani, Riri Novianti, and New Harman. Thirdly is drug design and organic synthesis. led by Professor Adil Zamri, Professor Jasril, and Dr. Yum Erianti. Fourthly is Petroleum and Biofuel Chemistry, led by Dr. Sofia Anita and Rizal Mahidin Tambusai. Fifthly is Adsorbent Coagulant and Biocomposite, led by Dr. Mudarina, Halida Sofia, Ganisvia Kartika, Pepi Halsayanti, Tengku Ariful Amri, Tengku Abu Hanifah, Itnawita, and Muklis. Our students has received numerous awards such as Funded Research by Ministry of Education, Novice Runner-Up of NUDC 2019, Second Runner-Up of National Chemistry Olympiad by MIPA Expo, winners in some paper competitions, and many more to come. We are so honored and thrilled to welcome you on board with us.
We apologize for the inconvenience and for the unpredictable error. Thanks to the committee. Let's move to the next agenda is opening remarks by the Organizational Board of Trustees of Chemistry Student Associations. Mr. Sony Ananta, time is yours.
Good morning, everyone. First of all, let us say thanks to God because the grace that has been given to us until today. Now we can attend here in the Zoom meeting for today HIMAKI International webinar. The honorable our speakers today, Mr. Nobutaka Yamanaka, PhD, Ohayo gozaimasu, Yamanaka-san, and the honorable the head of chemistry department, Madam Mudarina, the honorable to the all participants that has been participated today for the HIMAKI International webinar, and also I'm so happy and I'm glad of the committee because of their effort to make this HIMAKI International webinar success. Okay, so today we will have an international webinar about the theme Chem Talks Exit Application, Potential and Increase the Science Through Chemistry. So I hope with this webinar we can get some new knowledge and also new information for our research in Indonesia, especially for chemistry department in Rio University. And also I would like to say thanks to Mr. Nobutaka Yamanaka because of his time that available today to give us a new knowledge and new information about this kind of research. And also I would like to say thanks to the committee that has been given an extra effort to this event, and also all the participants. Yeah, I may suggest you to take some paper and a pen, yeah, to grab some note for this knowledge and information that will be delivered by our speakers today. And also, without any further ado, I will open this HIMAKI International webinar with a theme Chem Talks, Exit Expectation, Potential and Increase the Science Through Chemistry, with our speaker Nobutaka Yamanaka, PhD from Applied Chemistry Department, National Defense Academy, Japan. And with this, I'm Sony Anansa from the representative of Organization Advisory Board of HIMAKI Chemistry at FMIPA Universitas Riau, or your university, has been officially opened our HIMAKI International webinar with the theme Chem Talks, Exit Expectation, Potential and Increase the Science Through Chemistry, with Mr. Nobutaka Yamanaka, PhD, as speakers. Thank you for your attention, and I will bring back the stage to our Master of Ceremony. Thank you.
Start by a moderator, a college student from Chemistry Department, Riau University, and the speech will be delivered by our speaker, Dr. Nobutaka Yamanaka. And without any further ado, please welcome to our moderator, Sekar Fadilah. The stage is yours.
All right, thank you to the MC for welcoming me. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning, ladies and gentlemen. Welcome to this webinar entitled Bimetallic Catalyst for Chemoselective Transformation of Nitroaromatic Compounds by Dr. Nobutaka Yamanaka. I, Sekar Fadilah, as the moderator of our seminar today, am very pleased to see you all here and to welcome all of you in our webinar today. Okay, so our speaker today is Dr. Nobutaka Yamanaka. First, let's greet him. Good morning, doctor. All right. So,
good morning.
It is a great honor to have you here in our webinar today, doctor. Right. So, Dr. Nobutaka. Oh, okay.
Can I speak?
Yeah. You might respond that. Okay. So, Dr. Nobutaka Yamanaka is an assistant professor in National Defense Academy since October 2019. Besides that, he is also a tutor for international students in Chiba University, Japan from October 2016 to March 2018. He has received his bachelor degree in Applied Chemistry, Chiba University, Japan from April 2011 to March 2015. He has taken his master degree in Applied Chemistry, Chiba University, Japan from April 2015 to March 2017, and his Philosophy of Doctor or PhD degree in Applied Chemistry, Chiba University, Japan too, from April 2017 to September 2019. Some of his achievements are chemoselective hydrogenation of unsaturated nitro compounds to unsaturated amines by NISN alloy catalyst in 2018, chemoselective hydrogenation of unsaturated carbonyl and nitro compounds by Ni alloy and La oxide catalyst in 2019, and chemoselective synthesis of imine and secondary amine from nitrobenzene and benzaldehyde by Ni3SN2 alloy catalyst supported on TiO2 in 2021. He is also studied abroad at LIPI, Lembaga Ilmu Pengetahuan Indonesia, twice with the help of GASSO, Japan Student Services Organization, with the length of each stay was from October 2015 to November 2015, and from November 2016 to December 2016, respectively. All right, so there was a little bit information about our speaker today, Dr. Nobutaka Yamanaka. And now, let me welcome Dr. Nobutaka Yamanaka to deliver his presentation about bimetallic catalyst for chemoselective transformation of nitroaromatic compounds. To Dr. Nobutaka Yamanaka, the media is yours.
Can I speak on my topic?
Yes, you can.
Okay. Okay. You can see? You can see
Yes,
well?
Doctor.
Okay. Thank you for your introduction. I'm an assistant professor in Department of Applied Chemistry at National Defense Academy. I would like to thank you for giving me this wonderful opportunity today. As Miss Scar mentioned, I graduated from Chiba University, and Dr. Reo and I were in the same laboratory. Therefore, I'm very happy to see you again. The researches I'm going to talk about today were done with the help of these three previous laboratory members in Chiba University, Professor Shogo Shimasu, Professor Nobuyuki Ichikuni, and Associate Professor Takayoshi Hara. I appreciate their help. This presentation is composed of these 5 chapters. Chapter 1, Preamble. Chapter 2, Development of chemoselective nickel-sweetened alloy catalyst for the hydrogenation of 4-nitroserine to 4-aminoserine. Chapter 3, Development of highly active titanium-supported nickel-sweetened alloy catalyst for the chemoselective hydrogenation of substitute nitrogens. Chapter 4, one-pot synthesis of nitrogen-containing compounds from nitrobenzene and benzaldehyde by titanium-supported nickel-sweetened alloy catalyst. Chapter 5, summary. Before we move on to my topic, please let me ask a few questions. Sorry. What is a catalyst? Catalyst is a substance that increases the rate of a reaction and itself doesn't change before and after the reaction. There are 2 main types of catalysts, homogeneous catalysts and heterogeneous catalysts. A typical example of homogeneous catalyst is a molecular catalyst, which is called a homogeneous system because the catalyst dissolves in the reaction solution. Because the catalyst dissolves in the reaction solution. On the other hand, the representative of heterogeneous catalysts is solid catalysts, which are heterogeneous because the catalyst and the reactants are separate, such as solid and liquid or solid and gas. Here, let me ask another question. Which is actually used more in the world, molecular catalysts or solid catalysts? The answer is solid catalysts. Molecular catalysts have the advantage of precise control of chemical reactions, but also have the disadvantage that it is difficult to remove the catalyst after the reaction because the catalyst dissolves in the reaction solution. On the other hand, solid catalysts can be easily separated by filtration after the reaction. The recovered catalyst can be easily recycled, making it highly practical. However, it is difficult to selectively proceed only with a target reaction because compounds have various reactive function groups in the same molecule. Therefore, we came up with the idea of developing solid catalysts that selectively recognize specific function groups. This is what is referred to as chemoselective catalysts, as stated in the title. You can hear my voice well?
Yes, Doctor.
You can hear my voice well? Okay. Thank you. When when evaluating the catalytic performance of prepared catalysts, conversion, yield, and selectivity are mainly used. The equations used to determine each are as follows. Conversion equals mole of substrate consumed divided by mole of substrate fed multiplied by 100%. Yield equals mole of product produced divided by mole of substrate fed multiplied by 100%. Selectivity equals mole of product produced divided by mole of substrate consumed multiplied by 100%. And here, an example of a catalytic reaction is shown. So let's actually find the conversion, yield, and selectivity. If 0.8 mole of substrate A out of 1.0 mole is converted by a catalyst into 0.6 mole of product B and 0.2 mole of product C, the conversion of A, the yield of B and C, and the selectivity of B and C are as follows. Please confirm them now. If you have any questions, please tell me freely. The conversion of A equals 80%. The yield of B equals 60%. The yield of C equals 20%. The selectivity of B equals 75%. The selectivity of C equals 25%. You can calculate well. Any question? No? If no, let's get down to business, chapter 2. Development of chemoselective nickel sweetened alloy catalyst for the hydrogenation of 4-nitrosylserine to 4-aminosylserine. Aniline has been synthesized on a large scale since the early 19th century because it is an important intermediate for the production of agrochemicals, pharmaceuticals, pigments, and dyes. Nitrobenzene is one of the most abundant starting materials and is reduced to aniline by using stoichiometric reducing agents. These processes produce large amounts of byproducts, which can cause serious environmental problems. In contrast to the conventional synthetic method, transition metal catalysts such as platinum, palladium, lutetium, and nickel efficiently hydrogenate nitrobenzene to aniline. Thus, the catalytic hydrogenation of nitrobenzene has recently attracted great interest. Nevertheless, when reducing groups other than nitro group are in the same molecule, they show low chemoselectivity to the nitro group. Among these transition, hi. Yes, any question? Any question? Not yet.
I have a question.
Yeah, hi. Please tell me.
First, I appreciate to the panitia, Riau University, that make this seminar international. Amazing seminar.
Yeah.
Second, I want to ask you about your topic is bimetallics. What metal that you use?
Yes, bimetallic catalysts.
And second, how about 3-metallic, 4-metallic, bimetallic special for you? What is this special? That's my question. Thank you.
Please say again first question. Sorry, I cannot listen.
Yeah.
Sorry, I cannot listen your questions. Please tell me again. Sorry.
Your topic is about bimetallics. How about three
Yes,
metallic
bimetallic catalyst.
or other sums of metallic? Three metallic, four metallic, and what is the metallics that you use in your research? That's my question.
Bimetallic catalyst. Yes. Your question is why I chose a bimetallic catalyst, not three or four ingredient catalyst. I used bimetallic catalysts such as nicotine alloy catalyst. This is because the preparation, the catalyst preparation is more easier than three or four ingredient catalysts.
Pardon me.
I can answer.
What metal? What metal?
The question. Sorry, I misunderstood. Your question is what kind of metals that have been used? Yes. From now on, I will talk about. Okay.
Okay. Thank you. Next, continues your speaking.
My internet connection is unstable. Please say again. Sorry.
You might continue your speaker, Doctor.
Sorry. Among traditional metals, nickel is the most inexpensive one. Therefore, we aim to develop nickel-based solid catalyst that selectively recognizes the nitro group. The strategies include the addition of inorganic or organic modifiers, strong metal support interaction, and alloying with second metals. Alloying is an attractive strategy because it leads to the creation of new compounds that significantly modify the electronic and crystal structures of the parent metals. Inspired by the experimental study and the theoretical calculation that tin atoms preferentially interact with the oxygen lone pairs of the carbonyl group rather than olefin group, we aim to alloy nickel with tin to improve the chemoselectivity to the nitro group. We have succeeded in developing three types of nicotine alloys easily by co-precipitation method. Because of the simplicity and innovation of this preparation method, it is expected to be applied other alloys. First of all, tinkered the hydrolyzed solution was seated at room temperature for 48 hours to obtain the corresponding tin 4 plus solution. Then nickel 2 plus solution and tin 4 plus solution were mixed in predetermined mole ratios of 3.0, 1.5, and 0.75. The pH of the mixture was adjusted to 12 with sodium hydroxide solution. The resulting suspension was hydrothermally treated at 423 Kelvin for 24 hours to obtain the precursor, nicotine X catalyst. After the hydrogen treatment at Y Kelvin, the desired alloy catalyst, nicotine X HDY, was obtained. Figure 2.3 shows the X-ray patterns of the prepared catalysts. The untreated catalyst, nicotine 1.5, showed diffraction peaks characteristic to nickel sweetened alloy. Several unidentified peaks were also observed, but they disappeared after the hydrogen treatment at 673 Kelvin, suggesting that they are precursors of nickel sweetened alloy. The treated catalyst, nicotine 1.5 HD673, showed sharp nickel sweetened alloy peaks. The average nickel sweetened alloy crystal size was calculated from 101 plane of nickel sweetened alloy at 2 theta equals 30.8 degree, using Scher's equation. The growth of the crystal size of nickel sweetened alloy from 10.0 to 27.3 nanometers was clearly confirmed after the hydrogen treatment at 673 Kelvin. Next, the untreated catalyst, nicotine 1.5, was treated at different temperatures, such as 6 to 3 and 7 to 3 Kelvin. In two cases, distinct nickel sweetened alloy peaks were observed, and the crystal size of nickel sweetened alloy increased with increasing the hydrogen treatment temperature from 18.9 to 39.8 nanometers. For other mole ratios of 3.0 and 0.75, the untreated catalysts, nicotine 3.0 and nicotine 0.75, didn't show the corresponding alloy phases consistent with the mole ratios of the precursors introduced. But diffraction peaks derived from nickel sweetening 1 and nickel sweetening 4 were observed after the hydrogen treatment at 673 Kelvin. In summary, the importance of the hydrogen treatment process was clarified. The physical-chemical properties of the three types of nicotine alloy catalysts were investigated, and correlation between the nicotine mole ratios and the amount of hydrogen chemistry was found. The amount of hydrogen chemistry was decreased with increasing tin content because the addition of tin diluted the nickel adjacent sites required for the dissipative absorption of molecular hydrogen. To evaluate the catalytic performance of the prepared catalyst, the hydrogenation of 4-nitrosylene was used as a model reaction. The hydrogenation products are the target product for aminosylene, the byproduct for ethyl nitrobenzene, and the over-hydrogenated product for ethyl aniline. Firstly, monometallic nickel catalyst was applied to the model reaction under these reaction conditions, and hydrogenated the olefin group of 4-nitrosylene from the initial stage of the reaction, giving rise to the byproduct for ethylenitrobenzene. On the other hand, the alloying of nickel with tin suppress the formation of the byproduct for ethylenitrobenzene from the initial reaction stage, and showed 100% chemoselectivity to the target product for aminostyrene. This clearly indicates that the nickel sweetened alloy phase observed in the X-ray measurements plays an important role in the chemoselective hydrogenation of 4-nitrostyrene to 4-aminostyrene. The crystallinity of nickel sweetened alloy seems to be related to the efficient conversion of the nitro group, because the treated catalyst nicotine 1.5 HD673 showed a higher yield to the target product in a shorter reaction time than the untreated catalyst nicotine 1.5. For the treated catalyst, the yield of the target product for aminostyrene drastically increased with increasing the reaction time, and finally reached a maximum yield of 87% after reaction time of 11 hours. The effect of hydrogen treatment temperature on the hydrogenation of 4-nitrostyrene is shown in table 2.3, which includes the reaction time, the particle size of nickel sweetened alloy, the conversion, the yields of the target product, the byproduct, and the over-hydrogenated product, and the chemoselectivity to the target product. The treated catalyst at lower temperature showed high catalytic activity, but low chemoselectivity to the target product, suggesting that nickel 0 is in the catalyst. On the other hand, the treated catalyst at higher temperature showed slightly lower chemoselectivity to the target product. This is reasonable because the hydrogenation rate of olefin group accelerates particle size, as seen in showing the product distribution. The results of the application of other nicotine catalysts to the model reaction are shown in table 2.4. When the untreated catalysts, nicotine 3.0 and nicotine 0.75, were treated with hydrogen, the model reaction proceeded well, because the corresponding alloy phases, nickel 3.1 and nickel 3.4, were observed in the X-ray measurements. Focusing on the product distribution, nicotine 0.75 HD673 alloy catalyst gave the over-hydrogenated product for ethylene from the early stage of the reaction, suggesting that nickel 0 is mixed in. The reaction result of the three types of nicotine alloy catalysts were compared with their physical chemical properties, but no correlation between them could be found. In conclusion, nicotine 1.5 HD673 alloy catalyst showed the highest catalytic activity for the chemoselective hydrogenation of 4-nitrostyrene to 4-aminostyrene. Finally, we optimize the reaction conditions. First of all, the hydrogen pressure dependence was investigated, and it was found the chemoselectivity to the target product decreased with increasing the hydrogen pressure, but rather the reaction time was significantly shortened, indicating a significant increase in activity. This may be related to the increase in the amount of hydrogen dissociatively adsorbed adsorbed on the surface active leukocytes. Next, when the reaction temperature was lowered from 423 to 383 Kelvin, the yield of the target product, the target product was obtained almost quantitatively after a reaction time of 26 hours. However, the reaction time was very long, and therefore the optimized hydrogen pressure reaction temperature were 3.0 megapascal and 423 Kelvin, respectively. In summary, the three types of nicotine alloys, nicosweetin 1, nicosweetin 2, and nicosweetin 4, were prepared by co-precipitation method. Nicotine 1.5 HD673 alloy catalyst showed the highest catalytic activity for the chemoselective hydrogenation of 4-nitrosylene to 4-aminosylene under these reaction conditions. The decrease of the reaction temperature to 383 Kelvin derivative 4-aminosylene almost quantitatively. From the above, we select the catalyst that selectively recognizes the nitro group. However, the catalytic activity was relatively low, and therefore we next aimed to improve the catalytic activity. Afterwards, we denoted nicotine 1.5 HD673 as gosweetin 2. Chapter 3, development of highly active tightening supported nicosweetin 2 alloy catalysts for the chemoselective hydrogenation of substituting nitrogens. One of the strategies to improve the catalytic activity is the addition of Lewis acids into the reaction system. Lewis acids interact with substrates and intermediates to weaken NO bond, thus promoting the chemoselective hydrogenation of substituting nitrogens. However, the presence of Lewis acids affects the purity of the target product and can cause serious environmental problems. The transition from bulk to nanoscale is expected to increase the catalytic activity because it increases the fraction of atoms exposed over the catalyst surface. Therefore, we aim to develop nicosweetin 2 alloy catalysts supported on various metal oxides. Various metal oxide supported nicosweetin 2 alloys were prepared by the addition of these metal oxides as supports prior to the precursor precipitation with sodium hydroxide solution. All the supported nicosweetin 2 alloy catalysts showed broad nicosweetin 2 alloy peaks, which can be expected to reduce the particle size of nicosweetin 2 alloy. Actually, the physicochemical properties of the supported catalysts showed smaller particle size and higher hydrogen and CO chemistry than the unsupported one, indicating that the nicosweetin 2 alloy particles were highly dispersed on the metal oxides. The result of the application of the supported catalyst to the model reaction are shown in table 3.3, which includes the reaction time, the amount of hydrogen chemistry, the conversion, the yield of the target product, the byproduct, and the over-hydrogenated product, and the chemoselectivity to the target product. The supported catalyst suppresses the formation of the byproduct for ethylene-nitrobenzene from the initial reaction stage and showed 100% chemoselectivity to the target product. This is due to the nickel-sweetened alloy phase observed in the X-ray measurements. By prolonging the reaction time, titanium-supported nickel-sweetened alloy catalyst showed the highest catalytic activity without losing the high chemoselectivity to the target product. It means that we succeeded in developing highly active nickel-based solid catalysts for the chemoselective hydrogenation of 4-nitrostyrene to 4-aminostyrene. We also found a correlation between the catalytic activity of the supported catalyst and the amount of hydrogen chemosorption. From the viewpoint of industrialization, its stability and the range of substrates have to be investigated. The best catalyst, titanium-supported nickel-sweetened alloy catalyst, could be reduced at least 2 times for the model reaction, but the catalytic activity gradually decreased. The XRD results of the catalysts, the XRD results of the catalysts before and after the reuse didn't show any significant difference. Therefore, the decreased catalytic activity might be related to the oxidation of the surface active nickel sites that dissociatively adsorb molecular hydrogen. Subsequent application of the best catalyst to the hydrogenation of various substituted nitrogens gave the corresponding amino acids with high chemoselectivity, indicating the effectiveness of the best catalyst on a laboratory scale and its potential for industrialization. In summary, various metal oxide supported nickel-sweetened alloys were prepared by co-precipitation method, similarly to the unsupported one. For the hydrogenation of 4-nitrostyrene, loading nickel-sweetened alloy on titanium support for the hydrogenation of 4-nitrostyrene, loading nickel-sweetened alloy on titanium support significantly improved the catalytic activity with a similar chemoselectivity for the nitrile group to the unsupported one. The best catalyst showed good reusability for the model reaction and wider substrate scope. In Chapter 4, titanium-supported nickel-sweetened alloy catalyst was applied to the one-pot synthesis of nitrogen-containing compounds from nitrobenzene and benzaldehyde. Imines are important nitrogen-containing compounds used in many organic reactions as electrophilic reagents. Imines are conventionally synthesized by the condensation of amines with carbonic compounds, the oxidation of the corresponding secondary amines, the direct synthesis from alcohols with amines. One-pot amination of carbonic compounds directly using nitrile compounds is an attractive synthetic method because it doesn't require the prior reduction of nitrile compounds. In this study, we use the one-pot imine synthesis of benzaldehyde directly using nitrobenzene, nitrobenzene as a model reaction. Since the condensation between aniline and benzaldehyde proceeds spontaneously, efficient one-pot imine synthesis requires the preferential hydrogenation of nitrobenzene over benzaldehyde. Therefore, tightly supported nickel-sweetened alloy catalyst is expected to play an important role in this process. We firstly carried out the one-pot imine synthesis. In 1,4-dioxane solvent with equivalent amounts of nitrobenzene and benzaldehyde, and these reaction conditions. Nitrobenzene was preferentially hydrogenated to aniline from the initial stage of the reaction, resulting in successful one-pot imine synthesis. However, the same amount of aniline as that of imine was obtained, suggesting that the condensation reaction of aniline with benzaldehyde doesn't proceed well in 1,4-dioxane solvent. When the reaction time was further increased to 24 hours, almost no imine was obtained, and the over-hydrogenated product, secondary amine, was obtained in 50% yield. At the same time, a large amount of benzyl alcohol was produced as a byproduct. Therefore, we next aimed to carried out the one-pot imine synthesis using other solvents, such as protic polar solvents, aprotic polar solvents, and non-polar solvents. The reaction results are shown in table 4.1, which includes the conversion of benzaldehyde, the yield of the target product imine, the over-hydrogenated product secondary amine, and the byproduct benzyl alcohol, and the selectivity to the target product imine. After a reaction time of 12 hours, the use of protic polar solvents such as methanol and ethanol produce the highest catalytic activity, but had a negative impact on the selectivity to the target product imine. This is probably due to a strong interaction between protic polar solvents and the carbonyl group of benzaldehyde by hydrogen bonding. The catalytic activity of this alloy catalyst in a protic polar DMS solvent was next to protic polar solvents. The use of other aprotic polar solvents, such as THF, triethylamine, and 1,4-dioxane, showed low to moderate catalytic activity. This is probably due to the strong interaction between This is probably due to the strong interaction of the solvent molecules on catalyst surface. This is probably due to the strong interaction of the solvent molecules on catalyst surface, blocking the accessibility of the surface active nickel sites. Non-polar solvents such as orzarin, methylene, and paraxylene showed a lower catalytic activity, but provided the target product imine in higher yield when compared with a protic polar DMS solvent. Here it can be concluded that the catalytic activity was higher in a more polar solvent with the following order: protic polar solvent, aprotic polar solvent, non-porous solvent. And next, when the reaction time was increased to 24 hours in non-porous solvents, methylene gave the target product almost quantitatively, and therefore was found to be the best solvent. When the reaction time was further increased to 36 hours, the over-hydrogenated of 80%. Secondary amines are also essential nitrogen-containing compounds because they serve as intermediates for biologically active substances. Therefore, the control of the reaction time enables highly selective synthesis of amines and secondary amines. Finally, we optimize the reaction conditions. Increase the hydrogen pressure from 0.6 to 2.0 megapascal. The catalytic activity of this alloy catalyst was significantly increased, but the amount of the imine yield was only 8% at hydrogen pressure 2.0 megapascal. Next, when the reaction temperature was increased and hydrogen pressure 1.0 megapascal, the same behavior was observed as before. Therefore, the optimized hydrogen pressure and reaction temperature were 1.0 megapascal and 4 to 3 Kelvin, respectively. In summary, methylene was the best solvent for the one-pot imine synthesis from nitrobenzene and benzaldehyde by titanium-supported nickel-sweetened alloy catalyst, and a significantly high yield of 90% was obtained after reaction time of 24 hours, produced a relatively high yield of 80% to the corresponding secondary amine. Chapter 5, summary. In this presentation, successful development of the 3 types of nicotine alloys, nickel-sweetin 1, nickel-sweetin 2, and nickel-sweetin 4, easily by co-precipitation method. Among them, nickel-sweetin 2 alloy catalyst shows the highest catalytic activity for the chemoselective hydrogenation of 4-nitrostyrene to 4-amylostyrene under these reaction conditions. After reaction time of 11 hours, the conversion and the chemoselectivity to the target product were 100% and 87% respectively. It means that we succeeded in developing nickel-based solid catalysts that selectively recognizes a nitro group. However, the reaction time however, the catalytic activity was relatively low, and therefore we next aimed to improve the catalytic activity by supporting nickel-sweetened alloy particles on various metal oxides. As a result, titanium-supported nickel-sweetened alloy catalyst showed the highest catalytic activity without losing the after reaction time of 2.5 hours. The conversion and the chemoselectivity to the target product were 100% and 17% respectively. This alloy catalyst was next applied to the one-pot synthesis of nitrogen-containing compounds and these reaction conditions. After reaction time of 24 hours, the target product imine was obtained in an excellent yield of 90%, and the reaction time was further increased to 36 hours. The corresponding secondary amine was obtained a high yield of 80%. These results have already been presented in international conferences and published in journals, respectively. I'm sorry, I spoke too fast. Please do not hesitate to ask me if you have difficulty hearing or understanding. Thank you for listening to my presentation to the end.
All right, so that was the presentation from Dr. Nobutaka Yamanaka with bimetallic catalyst for chemoselective transformation of nitroaromatic compounds. That was such a great presentation, Doctor. It was so informative and so interesting to hear this chemoselective transformation by using bimetallic catalyst. Okay, so now we'll be going to the next session, which is question and answer session. In this session, I will allow some of our participants to ask their question to Dr. Nobutaka Yamanaka with his presentation. And to all of the questioners, please type at the chat box permission to ask _ your name, permission to ask _ your name. And when I already welcome you to ask your question, please open your camera and on your microphone so that you can ask your question directly to Dr. Nobutaka Yamanaka. And also, the committee already prepared 3 gifts for the first 3 questioners that come to our chat box. So make sure to type your permission to ask _ your name directly as soon as possible to get these 3 gifts that the committee already prepared for the first 3 questioners. All right, it's all right. We already have the first questioner, which came from Iren C. Anissa. To Iren, you might ask your question directly. Please open your camera and on your microphone to ask your question directly to Dr. Nobutaka Yamanaka. To Iren, please.
Okay. Hello.
Hello.
Okay. Can you hear my voice well?
Yes, well.
Okay. Okay. Before I ask my question, I would like to say thank you for Sekat place me to question directly my question. And thank you for Mr. Yamanaka for your presentation. So I would like to ask you that, is there any kind of chemical reaction that will occur faster without catalyst than with catalyst? I mean, we know that generally this kind of catalyst is materials that we use to make a chemical reaction going faster. But is there any exception about that? Like, is there any chemical reaction that will occur faster even without any catalyst? That's my first question. Thank you.
Thank you. Oh, sorry. Sorry. Please wait. What? Oh, sorry. The halogenation of 4-aminoserine, for example, without any catalyst, doesn't proceed any reactions. Even the halogenation of 4-aminoserine to 4-aminoserine. In summary, with catalyst, the halogenation of 4-aminoserine to 4-aminoserine proceed, such as nicotine catalyst. In the case of no catalyst, any halogenation reaction doesn't proceed. Okay?
Okay. Yeah, I understand.
You have any questions?
No, I think that's enough. Yeah. Okay. I actually have a second question. Moderator, am I allowed to ask my second question?
Yes, you might.
Okay, thank you so much. Okay, sir. So now I'm kind of having an experience for my last project for the college. I made an adsorbent from palm tree, and I used the fiber of the palm tree to make this adsorbent. And I used this activated carbon for paint industrial waste. I used it to absorb the metallic materials that contain in that paint industrial waste, such as zinc, such as chromium. And my question is, this activated carbon will be activated with some activators that I believe this activators is working as well as how the catalyst work. I mean, it has the same principle of works. So could you show me the parameters how we choose and how we choose a catalyst for our chemical reaction or our chemical process? Like from the parameters, we can conclude that it will have a good result in the end. Can you get it? Do you get it?
You want to remove
metallic materials.
Materials from solution.
What? I'm sorry.
You want to remove the metal from any solutions?
Yes. Yeah.
With activated carbon.
Yeah. Yeah. All right.
Sorry. My major is catalysis and preparation catalyst, and so I cannot answer your question well.
Okay.
Sorry.
Yeah. Okay. It doesn't matter. My mistake, maybe. Yeah, I kind of a little bit confusing about this. Like, I mean, I couldn't make any differences between this activator and catalyst. Okay, it's from you. It's okay. It's fine. Thank you so much for your explanation. Thank you for Mr. Yamanaka and moderator.
Terima kasih.
All right. We will wait for the second questioner. To all of the participants, if you have any question, please type at the chat box permission to ask _ your name, permission to ask _ your name, and then when I already welcome you to ask your question, please open your camera and on your microphone to ask your question directly to Dr. Nobutaka Yamanaka about his presentation. Is there no question again? Don't forget that the committee already prepared 3 gifts for the first 3 questioners. So if you have any question to Dr. Nobutaka Yamanaka about his presentation, you might type permission to ask _ your name in the chat box.
I have a question for Mr. Yamanaka.
Okay, please.
Directly. Okay, thank you. Hisashiburi desu, Yamanaka-san. Can you hear
Ryo-san,
my
hi.
voice? Okay.
Yes.
I have a question about your presentation. In many cases, you use titanium dioxide as a support catalyst, right? Well, why you choose titanium as support compared with alumina, silica? Why titanium is the best support for this nicotine catalyst?
Yeah.
Thank you very much.
Okay. Thank you for your question. Please wait. Please wait. Wait. Yeah. As you said, titanium supported nickel sweetened alloy catalyst shows the highest catalytic activity for the chemoselective hydrogenation of tessarine to 4-aminosarine. Compared with the other metal oxides, titanium have relatively smaller surface area, as shown in table. You can see.
Yes. Please.
You can see this table. Yes.
Yes. Sir.
Yes. Alumina has the highest surface area among them, but titanium supported has a relatively smaller particle surface area of 14. So we suggest that the spillover, the degree of the spillover is larger compared with alumina. So titanium supported nickel sweetened alloy catalyst shows the highest catalytic activity among them. Therefore, we used the best catalyst to other reactions. This is my answer for your question.
Okay, so the titanium supported catalyst has the highest hydrogen uptake. What about the particle size or crystalline size of nicotine alloy catalyst from XRD pattern? Could you show me the XRD pattern of this catalyst?
Yes. Here, the extract pattern is shown in figure 3.2, and the particle size is shown in table 3.2. Yes, the correlation between the catalytic performance and particle size could not we didn't obtain the correlation between the catalytic activity of the supported catalyst and the particle size. So we concluded that we explored the other parameters such as hydrogen and CO chemistry option. You can hear my voice?
Okay, very clear. Okay, thank you very much for your answer, Yamanaka-san.
Hi. Hi.
All right. Now for the third questioners. For the third questioner is come from Yola Mesa in Vienna. To Yola Mesa in Vienna, please open your camera and on your microphone so that you can answer your question directly to Dr. Nobutaka Yamanaka. To Yola Mesa in Vienna, please. Yola Mesa in Vienna. Did you have any connection problem? If you have any connection problem, please tell us in the chat box. Yola Mesa in Vienna. Well, all right. So it's okay. So for Yola Mesa in Vienna's question is how a catalyst can increase the rate of a chemical reaction, and what is the difference between a reaction using a catalyst and not using a catalyst? To Dr. Nobutaka Yamanaka, please.
How a catalyst can reaction? Generally speaking, the adsorption is a key factor to increase the rate of chemical reaction because, for example, the halogenation of phenolphthalein, the nitric group can adsorb on the catalyst surface via oxygen atom. Thus, the NO bond can be activated. Therefore, the reaction proceeds well. I can answer well about for first question.
To Yola, you may respond it. Okay. To Yola, you may respond it in the chat box. It's already enough. You can say that it's enough in the chat box. All right. While we're waiting for the Yola Mesa in Vienna's response, let's go to the next questioner, which is come from Alfida Rahma. To Alfida Rahma, please open your camera and on your microphone so that you can ask your question directly to Dr. Nobutaka Yamanaka. To Alfida Rahma, please.
Can I question here? Sorry. Can I answer here?
To Alfida Rahma.
Sorry.
Okay.
My question has been answered by the previous asker. Now I wanna asking about what are your problem in doing this research. For example, in the case of the separation of impurities, maybe in the catalyst. Thank you.
Sorry, can I say again?
What are your problem in this research? Maybe for example, like a separation of impurity in the catalyst. Thank you.
Sorry. I have enough. I have enough ability to understand your question. Please, someone help me.
Okay, Alfida Rama, is your question about what is the problem with while this Dr. Nobukitaka Yamanaka doing his research? Is that kind of question?
During my research, my problem, my difficulty.
Pardon me?
My problem about this research.
Yeah, it's something like that.
Research difficulty. Yes. I will introduce my problem. One problem. The problem is the selectivity to the target product because tightly supported nickel sweetening catalyst showed good catalytic activity, but the selectivity is lower 80%. So this is my problem, and I think that we think that we aim to improve the chemoselectivity to the target product by using a novel approach. Yes. It's my one problem is to find the selectivity to find how to increase the selectivity by some methods. Okay.
Okay, so you have a problem about the selectivity of the catalyst, right?
Yes.
Okay.
Okay. So now we'll be going to the next questioner, which come from Dia Permatasari. To Dia Permatasari, please open your camera and on your microphone to ask your question directly to Dr. Nobutaka Yamanaka. To Dia Permatasari, please. All right, since Dia Permatasari connections looks bad, I will read the question in the chat box. What is meant by activity energy? Then what is the relationship between activity energy and catalyst? To Dr. Nobutaka Yamanaka, please.
Activation energy. activation energy. Activation energy. Sorry. We have not yet find the activation energy for the hydrogenation of phonatathione. We carried out the experimental by using our hands. So I want to carry out the theoretical calculation using DFT calculation method. So now I cannot answer your question well. Sorry.
Well, I'm sorry, doctor, but maybe this question means that what is the definition of activation energy, and then what this relationship between this activation energy and then catalyst, something like that.
Activation energy.
So it's like the definition of this activation energy and then the relationship between this activation energy and the catalyst.
Activation energy. And this figure, this figure can solve he or she his or her question.
Yeah, about the definition of the activation energy. So what is the activation energy is something like that.
Activation energy definition. Generally, the reactants is converted into product via a volcano curve. The difference between the top of the volcano and the energy level of results is defined as activated energy. This question is enough.
To Dia Permatasari, if you think that it is enough, please respond in the chat box so that we could know that you already understand with, the answer. Okay. Now we will be going to the next questioner, which came from Novita. To Novita, please open your camera and on your microphone to ask your question directly to Dr. Nobita Kayamanaka. To Novita, please. All right. So the question from Novita is, does the activation energy affect the catalyst? And can you explain what the effect of this activation energy in catalyst? To Dr. Nobita Kayamanaka, please.
Sorry, please say again.
Okay, so the question from Novita is, does the activation energy could affect the catalyst? And can you explain what kind of effect that this activation energy could affect the catalyst?
The question is what parameters affect the reaction results?
Maybe it could be something like that in the reaction. Yeah.
In our experimental, some parameters affect the reaction results, such as catalyst loading amount, or catalyst or substrate loading amounts, hydrogen pressure, and reaction temperatures, and so on. This answer is enough.
Novita, how about it? If you think it is enough, please answer it in the chat box. All right, while we're waiting for the Novita's response, let's go into the next question, which came from Fuji Randa Lumban Gaul. To Fuji, please open your camera and on your microphone to ask your question directly to Dr. Nobutaka Yamanaka. To Fuji, please. Fuji, well, your question, it looks like same as the previous question. Would you like to ask another question?
Yes, I want to ask another question.
Okay, so Fuji, please.
Okay, for my question is, what are the alternative catalysts if you cannot find a nickel zinc catalyst?
Your question is, have you ever developed other catalysts? You can hear my voice?
Can you repeat again?
Yeah. Your question is, have you ever developed some other catalysts?
Yes, that's.
In this presentation, we introduced the development of nicotine alloy catalysts, but now we have already developed other nickel-based biometallic catalysts, such as nickel iron, nickel iridium, and nickel magnesium. Okay.
Okay, doctor. Thank you for your answer.
All right. For the next questioner is come from Eva Amalia Arsenti. To Eva Amalia Arsenti, please open your camera and on your microphone to ask your question directly to Dr. Nobutaka Yamanaka. To Eva Amalia Arsenti, please.
Okay, my name is Eva. My question is, what is the role of a catalyst in the course of a reaction? Thank you.
Yeah. Yes. As shown in figure 2.7, only nickel catalysts hydrogenated the nitric group and olefin group of 4-nitrosylene, but the addition of tin into nickel suppresses the formation of the byproduct for ethylene-nitrobenzene, leading to the excellent synthesis of the target product for aminostyrene via the via the electrostatic interaction between the catalyst surface and nitro group. Okay, you can make sense.
Okay, that's enough. Thank you.
Okay, now for the last questioner that come in the chat box is from sitting down. To sitting down, please open your camera and on your microphone to ask your question directly to Dr. Nobutaka Yamanaka. To sitting down, please. To sitting down, do you have any connection problem? If yes, you can type that in the chat box so that all of us can know it, and I will read your question in the chat box. Sitting down. All right, well, sitting down's question is, could you explain the difference of XRD for nickel syn without and with catalyst in different temperature? Thank you before. To Dr. Nobutaka Yamanaka, please.
I cannot understand this question because without and with catalysts in different temperatures, what is the without?
Maybe it's like what is the different XRD for nickel syn using catalyst and not using catalyst by different temperature?
At various temperatures. I'm sorry. He or she may be misunderstood because to obtain nicotine alloy catalyst, the process of the hydrogen treatment is necessary because to reduce the surface the surface of the precursors. So we only carried out the treatment at different temperatures. So in our case, the reduction of catalyst is necessary to obtain nicotine alloy catalysts. Okay.
Well, all right. To sitting down, is it enough for you? Okay, well, is there any question again? If you have any question, please type permission to ask _ your name in the chat box. All right. So we already have from Ferel Faturendika. To Ferel Faturendika, please open your camera and on your microphone so that you can ask your question directly to Dr. Nobutaka Yamanaka. To Ferel, please.
Okay, thank you for the chance. Hello, doctor. I want to ask you that from the beginning presentation, I read from your presentation that there is a sentence about the idea of developing solid catalysts that selectively recognize specific functional groups. I'm sorry, personally, I'm sorry if I didn't get the meaning, but can you just give me more explanation about that sentence, sir? Thank you.
This part. This presentation slide.
It was from the chapter 1, doctor. Chapter 1, preamble.
Chapter 1?
Yes. Chapter 1.
Yes. Please introduce again. Homogeneous catalysts have the advantage and disadvantage, but solid catalysts have disadvantage and the advantage. So we want to develop solid catalysts only. We aim to develop solid catalysts possessing high selectivity and easy separation and simple recycling. We came up with the idea of developing 3D catalysts that selectively recognizes specific functional groups. I can answer your question well.
Yeah.
Solid catalysts have the characteristics of this point, but show low selectivity to the target reaction. So we aim to develop solid catalysts that facilitating the specific reaction.
Okay, doctor. So that is the meaning of the idea of developing, right?
Yes.
Okay. Okay, thank you, doctor.
Okay, and the next question is come from Mr. M. Rizal Tambusai. To Mr. M. Rizal Tambusai, please.
Thank you very much for the chance for me to question to Mr. Nakabata. I want to ask you, can Indonesian chemistry student continue their chemistry education in your university in Japan, like master or PhD? And second, what is your catalyst crystalline structure? Like Bernesite or cryptomelon, the structures of your crystal relation to the activity catalyst. I think there is a relation, yeah. What is the relation? And you always say about the one pot imine. One pot imine. What means a one pot imine? It's better than other pot. That's my question.
First question is that in Japan, PhD can be taken in every university.
Riau University. Same with Leo. Leo from Chiba, PhD. Mr. Sogun, his teacher.
Yes, in Japan, PhD can be taken in every universities.
Yamada-san, about the foreign students at National Defense Academy. So at this academy only for Japanese, or maybe some Indonesian can continue their study at National Defense Academy? I think only for Japanese, right? Or
Yes. National Defense Academy of Japan.
Oh, only for Japanese?
Yes, only Japanese maybe.
Oh.
But in National Defense Academy, sometimes the conference will be held from overseas, such as America and Europe. So maybe other national defense academies is located in many countries, but I don't know well.
Yeah, okay, thank you for the information. Before this, my junior Leo graduate PhD from Chiba University, paid by his teacher, Mr.
Professor Shogashimazu.
Shima Sensei.
Shima Sensei.
Chiba City, yeah? He ever
Because
come to...
Chiba University is public university, right? Yeah, so everyone can.
Yes.
Indonesian student needs to continue the education with free program for PhD. Thank you for you're from defense military university, maybe. Only for Japanese, eh?
Yeah.
Okay, thank you.
Second question about the relationship between the crystal structures and their kinetic performances.
Yeah, the structures.
Yeah. Yes. Yes. We have already compared the kinetic performance of the prepared catalysts with their corresponding crystal structures, but no correlation between them. So, there are one point to be solved from now on. we cannot unveil the relationship between them. You can hear.
Yeah.
And we cannot. We have already compared the catalytic activity of the prepared catalyst with their corresponding catalytic crystal structures, but we couldn't obtain the correlation between them. So we have to unveil the relationship of the catalytic activity and other parameters.
Okay, thank you.
And third question.
One pot imine.
Yeah.
You always say that looks like the best. Why? One pot.
One pot. Generally, the synthesis of imines includes the condensation of amines with carbon compounds. But in my presentation, in my study, we carried out the one-pot imine synthesis of benzaldehyde directly using another compounds, but not primary amines.
Okay, thank you, Mr. Thank you for your answer. Maybe we can make a next relation.
Thank you for your questions.
For the next questioner, come from Muhammad Haikal Zikra. To Muhammad Haikal Zikra, please open your camera and on your microphone so that you can ask your question directly to Dr. Komputer Kaya Menaka. To Muhammad Haikal Zikra, please.
Okay, thank you to the moderator for allowing me. So, is my voice heard clearly? Can you hear me?
Yeah.
Okay, I have a question, sir. Previously, you use nickel tin catalyst. Then, when my friend asked Fuji asked about alternative catalyst, and you mentioned about nickel aluminum, right? If I'm not mistaken. So, and my question is, do the alternative catalyst you mentioned early that nickel aluminum that have the same effectiveness?
Oh, yes. Yeah. The addition of tin to in our study, the addition of tin to nickel induce the electron transfer from tin to nickel. Alumina also can cause the electron transfer from aluminum to nickel. So I think that nickel or alumina alloy catalysts can hydrogenate the nitric group preferentially than the olefin group. So nickel alumina alloy catalyst is expected to be efficient for the chemosynthetic hydrogenation reactions. Okay.
Okay, thank you, sir. Thank you for your answer.
All right. Well, if there are any question again from the participants, if you have any questions, please type permission to ask _ your name, permission to ask _ your name in the chat box, so that I would know that you want to ask question to Dr. Nobutaka Yamanaka about his presentation. Is there no other questions? Okay, well, I will wait 1 minute, and if there is no other question, we'll go into the next session. Well, all right. It looks like there is not any other questions. And all of the questions already answered directly by Dr. Nobutaka Yamanaka. Thank you so much, Doctor. And thank you so much for all of the questioners for your questions. And also congratulations for the first 3 questioners, which is Iren, Dr. Leo, and then Yola. For these 3 winners, please contact our committee to get your gifts. You may contact the committee by direct messaging them in this Zoom cloud meeting, and make sure that you text the right person, which is our committee, to get your gifts. And now we will be going to the next session, which is giving the placards to our speaker, Dr. Nobutaka Yamanaka. So to the committee, please.
Oh, sorry. First, should I talk about? Huh?
Yes, Doctor. So this is the placards from the committee that will be sent to your email by our committee. Thank you so much, Doctor, for your presentation today. It's so informative, so much knowledge that you could take in this presentation today. Okay. So, well, this is the placards that we give via online, but there will be placards via your email that will be sent by our committee. And well, all of the discussion session of today's webinar already end, which is my job as the moderator already end too. But before I close, I'd like to say thank you to all of the participants for your participation, and to all of the questioners for your questions. And don't forget for the winners, the first 3 questioners, Iren, Dr. Leo, and then Yola, to contact our committee to get your gifts. And then especially to Dr. Nobutaka Yamanaka, thank you so much, sir, for your great presentation today about this bimetallic catalyst for chemoselective transformation of nitroaromatic compounds. Thank you so much, sir. And thank you so much for all of the participants, for all of the questioners. And also, I'd like to apologize if I have any mistake during our seminar today. My apologize. Lastly, stay safe, stay healthy, stay spirit, stay strong. Have a nice day. Wassalamualaikum warahmatullahi wabarakatuh, and good morning, ladies and gentlemen. I'll bring back this media to our MC. So to our MC, please.
Okay, thank you to our moderator. We are so grateful. Thanks for excellent presentation by our speaker, Dr. Nobutaka Yamanaka. And thanks to moderator Sekar Fadila who has led this session to make it conducive. Finally, we arrive at the end of this event, but the last but not least, we will going to the photo session. So for all participants, please turn on your video because the committee will screenshot our screen. Okay, please for all participants to turn on your video. All right, in my comment, for the first page, please keep smiling and 3, 2, 1.
Can I close?
Oh, wait, sir. We will take a photo session or some documentation for this webinar. Okay, to the committee, please take a screenshot in my comment. 3, 2, 1. Okay, we're going to the second page. In the participant in the second page, please turn on your video. To the committee, please stand by for the screenshot. Okay, in my comment, 3, 2, 1. Okay, once again for the third page, to all participants in third page, please turn on your video and keep smiling. And in my comment, 3, 2, 1. Okay, I remind to all participants, we need your advice and suggestions regarding this webinar, so we will fill the form that we have sent on chat box. And for accept the certificate, you can check your email because the certificate will be sent automatically after you fill the questionnaire form. And the committee will send the questionnaire form in our chat box. So please fill that form because you will accept some certificate in your email. Okay, such as this webinar International, CHEM Talks exceeds expectation, potential, and increase the science through chemistry, with topic bimetallic catalyst for chemoselective transformation of nitroaromatic compounds. Thanks for joining our webinar. I'm Muhammad Abdul Karim as Master of Ceremony. Forgive for all mistake, keep healthy, goodbye, and see you next. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.